Alrighty, ladies, so we are going to work through 3 more example problems for solving exponential and logarithmic equations. And the first one that we're going to go through is actually from our 7.6 day 1 notes that we didn't quite get to in class. So this should be familiar if we took the time to read it in our notes, even though we didn't have a chance to solve it. So in example 1, we've got a scientist studying a virus at the CDC labs, and the virus replicates at such a rate that it can be described by continuous exponential growth. And so that tells us that we are going to be needing A equals PERT. And then from here on out, we have enough information where we can, okay, it looks like we're going to be solving for R and then plugging in something in from there. So there are 80 virins in her experiment when she begins. Well, if that's what she has when she begins, that's a value for P. That is an initial amount. So she starts with 80. Great. And then we have this ordered pair given to us next. So it takes 4 hours for the number of virins to double. So after a time of 4, it doubles. Okay, if she started with 80, double that would be 160. So with this information, we can now solve for R just by plugging everything in and solving from there. So we've got A equals 80 e to the RT, and now we can plug in our ordered pair, 4 for T, and then 160 for A. And now we can solve for R. Well, we can do that by first moving that 80 to the other side by division. So we divide both sides by 80, and we get 2 equals e to the 4r. And then from here, we would want to log loop it, and we can move the 2 to the other side. We always like our exponent on the left, and we have an exponent now, so we want to end with a log. So we want log base e, which we can just write as ln, of 2 equals 4r. So in order to get r by itself, we can either divide both sides by 4 or multiply both sides by 1 over 4. So our growth rate is going to be 1/4 the natural log of 2. And for the sake of giving us a number that would actually be useful, we will plug that into our calculator to get a decimal approximation. We find that our growth rate is about 0.17329. That does seem like a lot of decimals, but we do want to keep as many as possible because our R really plays a big factor in how our function changes. So the more decimals we can keep, the better. Now that we know R, we can answer our second question. So how many virins will there be after 10 hours? Well, our general equation is now A equals PE to the 0.17329 T. And for this particular case, we also know our principal amount. So we know that we can swap out P with 80. And now we can also swap out T for 10. Because we have a time of 10, we want to figure out how many we have to end with, which would be our A value. We can plug this straight into our calculator and make it do all the work for us. And we find that our final answer is 452.56-ish. But if we're talking number of virins, we can't have like 0.56 of a virus. So we would round up to the nearest whole number, 453 virins after 10 hours. In example 2, we have the equation given to us. So the population of the Hawaiian island Oahu can be described by the following continuous exponential growth function, where T is number of years since 1960. So our first question is, well, what was the population in 1960? Well, there's a couple different ways we can think about this. We can say, well, that's 635,000 e raised to the 0.018 times 0. Well, anything times 0 is just going to be 0. So we've got e to the 0th. Well, any value raised to the 0th power is just 1. So 635,000 times 1, our population was just 635,000 people. Now, we also could have thought about it in terms of, well, hey, this equation kind of looks like it's PERT with different variables. So instead of A, it's Y. But P is always our principal amount. So it would make sense that the amount that we have in front of E, the number in front of E, is going to be our principal amount, our initial starting value. Determining our population in 1970, well, if we remember that T is years since 1960, this would be T equals 10. So we've got, 635,000 times E raised to the 0.018 times 10. Again, make your calculator do all the work. You end up getting 760,233 point something. But again, we're dealing with population, so we would want to keep our answer as a whole number. So 760,233 people. When will the population surpass 1 million people? This is a question for our graphing calculator. So what we do is we plug in y1 equaling our function, 635,000 times e to the 0.018t. And then y2 is going to be that 1 million. And we want to know where they intersect. So our graph will look like this when we have these windows. And we are looking for that intersection point, so we would use the second trace, option 5, intersect option. First curve, second curve, guess. We find that we get 25.22946-ish years. So about 25 years later. And 25 years since 1960, we would take 1960 plus 25. It apparently surpassed 1 million people in 1985. I can only imagine what the population would be now. Lastly, we've got example 3, where we've got a bank manager investing $4,000 in an account that pays 3% interest compounded annually. Okay, if it's not compounded continuously, this tells us we need our first equation, A equals P, 1 plus R over N to the NT. Even more specifically, if it's compounded annually, remember N is the number of times per year, so we're going to let N be 1. And then this first sentence gives us a value for P, and our rate is always expressed as a decimal, so rate is 0.03. So we can take that first sentence and write it in an equation right now. So 1 plus our rate divided by the number of times per year it's compounded raised to the NT. Well, we've got a lot of ones in here, so we can actually simplify this just a touch. So we'll have A equals 4,000 times 1, 0.03 divided by 1 is 0.03. And then 1 plus 0.03 is 1.03 raised to the t. Okay. Next sentence, she also invests $2,000 in an account that pays 5% interest compounded annually. Okay, so it looks like she's got 2 different investments, and we want to know after what length of time will the 2 accounts have an equal balance. Okay, so let's think about our second investment first. So again, compounded annually, that's going to be the same sort of situation, just with slightly different values. So this time our initial investment is $2,000 and our rate is 0.05. But then other than that, we've still got 1 for the number of times per year it's compounded. So we can simplify this guy as well and say A equals 2,000 times 1.05 to the t. Well, we want to know when they have an equal balance. Well, A is our ending balance, so we want to know when those 2 things are going to be equal. Well, in order to do that, we are going to go to our graphing calculator. We are going to plug in this first guy for y1 and the second equation for y2. Our calculator doesn't really get the t's, so we can change them to x's. And we want to know when the y coordinates will be the same. Well, that's where your lines will intersect. So our graph ends up looking like this. I believe our blue line was our $4,000 investment at 3%, and And the red line is our Y2, our $2,000 invested at 4 or 5%. And it looks like they intersect after about 36 years. So it takes 36 years for that higher interest rate to end up giving you the same amount of money, since you deposited such a lesser amount of money to begin with. Your initial deposit was much smaller. So our final answer for this, we get about, not dollars, years. 36 years, and the balances will be the same.